All right. Okay. So what happened, if the request, less than available or equal is false based on this scenario. Okay, so P4 request 330. So now this is the comparing value. So after comparing, the result is false. So what happened? So P4, okay, cannot be granted since the resources are not available. And request for less than or equal available become false, so that this request has been unfulfilled. So here they said not fulfilled. All right. Okay. So another example that we do comparing, and now the result is true. Okay, so means here P0 requests 0 to 0. Yeah, and then this is available forward. Okay, since that requests less than and need less than or equal needs and requests less than available, so pretend this request has been fulfilled. So next, execute resource request algorithm. All right, yeah. So this is the table you can see here. All right. Okay, available. So available now is this. Okay. So the request is this from P0. So minus that, so you have this value 2, 1, and 0. Yeah, for each of the resources. All right. And then allocations, yeah, P0 will be allocation P0, P0, 0, 1, 0 is this, and also this. And then plus the request. The current request is 0 to 0, so it will become 0, 3, 0. The current request similar to this. And then, so now the value of allocation is 0, 3, 0. Yeah. So next, so the needs, yeah, is 0. Okay. Is needs a P0. So minus a request of P0. So here is the one, 743, which is need for P0, and then minus 0 to 0. So you will have, wait, request, request. So it becomes 7 is the needs. Yeah, 7 to 3 needs. Okay, current needs. And then, okay, change. You can see it change, right? So we change the allocation also, and we change the needs and also the available. Okay. So see this difference, and now change. All right. Okay. So here we look here. Okay, we change. I will change this, and then this allocations. All right, and needs. Okay, the allocations, and this for this. Yeah, for this. Okay. Right. And now we have P0 request is 0 to 0. Okay, for the each of the resources. So step 1, work equal available. Okay, is 201. And then what is the new safe sequence produced? Yeah, system will not grant the request of P0. Okay. And the request result unsafe state, although resources are available. Yeah. And then we look here. Okay. And available for the P0. Okay. So now goes to the next. Yeah. Okay. Now deadlock detection. Allow system to enter a deadlock state, and then detection algorithm, which is single instance of resource type. Yeah. And then multiple instances of resource type. On this is the numbers of, the recovery schemes that we found. Yeah. Okay. Yeah. So this is the deadlock detection, RAG, and deadlock detection algorithm. All right. So single instance of each resource type. Yeah. Deadlock can be detected by building resource allocation graph, RAG, that we used before. Yeah. So maintain a wait for graph. Yeah. And then nodes are processes. For example, PI to PJ. Yeah. If PI is waiting for the PJ. Yeah. Converting a resource allocation graph to a wait for. Okay, resource allocating, converting, yeah, converting the graph, this guy RAG graph to wait for graph. Okay, so this is the example. Yeah, all right. So from resource allocation graph to the correspond wait for graph. Single instance of each resource type. So maintain a wait for, yeah, graph. Periodically invoke an algorithm that search for a cycle in the graph. If there is a cycle, there is a deadlock. Okay, so an algorithm to detect a cycle in a graph require an order of n power of 2 operations, where n is the number of vertices in the graph. Example, the detection algorithm, yeah, can be explained by using RAG, resource allocation graph, and reducing them. The step to reduce a graph, yeah, first, find a process using a resource and not waiting for one, which is referred to figure 5.12b. Next, find a process that is waiting only for resources that are not fully allocated, which is figure 0.5.112c. And next, repeat step 1 and 2 until all lines removed, like figure 5.12d. Yeah? All right. So this is an example. This is a deadlock free. This system is a deadlock free because the graph can be completed, reduced, as shown in the. Okay, all right. Example, example, a graph remaining the deadlock using those steps. A, even after this graph, A is reduced as much as possible by removing requests from P3. Okay, it is still deadlock in B. Right? Okay, the one. And then next, several and multiple instances of a resource type. Let n number of processes and m equal number of resource type. So available vector of length m if available j equal k, then there are k instances of resource type rj available. So allocation n times m matrix. If allocation ij equal k, then pj, yeah, is currently allocated k instances of rj. And then for the request or variable request n times m metric, that indicates the current request of each process. If a request I and j equal k, then process P, yeah, is requesting k additional instances of resource type RJ. All right. So now detection algorithm. So let work and finish B vector of length M and also N. Yeah. So initialization first, work equal available. So for I, which is 1, 2 till N, yeah, if allocation not equal 0, then finish equal false. Otherwise, true. All right. Next, for an index I such that both finish and also request. Finish must equal to false. Meanwhile, request less than or equal works. If no such I exists, go to step 4. This. And then work equal work plus allocation. So finish equal true, and next go to step 2. Okay, yeah. And then if finish equal false, so for some I, yeah, which is in between between 1 to n, yeah, then system is in deadlock state. Moreover, if finish equal false, then pi, yeah, is deadlock. So deadlocked. Okay, all right. Next, 5 processes P0 to P4, 3 resource type, okay, A 7 instances, B 2 instances, and C resource with 6 instances. So similar like the previous one, they give this table. Okay, this is snapshot at time t0. Yeah, at the beginning of time. Yeah, similar scenario, similar. I mean, yeah, you can say that. right? So sequence, okay, P0, P2, P3, P1 will result in finish equal true for all I. Okay, yeah. So finally, yeah, sequence. So this is detail, yeah. That's okay. Step 1, similar that work equal available, so work equals 0, 0, yeah. They check all PI allocation, PI from P0 to P4. Is it allocation not equal 0? So if yes, yeah, we give, if yes, so like this, is it PI not equal 0? PI, yeah. Is it PI, each of these, okay, not equal 0, so is a false. They give example of this, okay, like every check, all not equal 0, so it's a false. Step 2, okay, request start with P0. Is request P0 less than a work? Okay, so P0 less than a work. So and then yes, go to step 3. Okay, all right. All right. Okay. So this is available. Okay. 0. So we'll compare with this. Okay. So the first of all is P like this, P0 first. So 0 to 1, similar that we yeah. So this request 0, 0. So we check the step 1 first, check the allocation first. Okay, and then false, yes, and then go step 2, request start with P0. Okay, and then if yes, this one, yes, P0. Yes, go to step 3 and then update the latest work. Okay, please go through this, yeah, and then go to step 2. Step 2 goes to the next one. Okay. Shall we previous? All right. Okay. So next, go to step 2. Okay. So process for P1 and check is request P1 less than work. Request P1. Yeah, less than work. Let's work this. Check. So no. So check P. Next P. Yeah. And then P2. After P1 put P2 and check if yes. This, go to step 3. Yeah. Then update. Yeah. Update the latest work. So the value is 312. And then finish P2 equal to request is fulfilled and go to step 2 again. Okay. Step 2, P3. Do it the same thing next on. Yeah. Go through this till the end. And then next. Okay. P2 request one additional instance of type C. Yeah. So, and then finally, we can see this P2. Yeah. Okay, finally, well, you can see that. Okay, so P1, we can see here is only one, resource. So state of system, is it system in a deadlock state? So can reclaim resources held by PO, but insufficient resource to fulfill other processes requests, and the deadlock actually exists, consisting of processes P1, P2, P3, and P4. Okay, because they are requesting, except for P0, no request. All right. Okay, so next is step 1. So work equal available. Yeah. So works is 0, 0. Check all PI allocation. So is it allocation PI not equal 0, equal false? Yeah. Check PI allocation. So P2 requests one additional instance of type C. Yeah. And then check. Okay. Here they check this with this, and then check one by one. Request start with P0, and then is a yes. So go to step 3, update, then assign that, and locations currently is 010, and then we change and go to step 2. So request start with P1, request less than work, yes, and then check, that is no, and then check P2, and then request start at P2. Where is it? Request P2 less than or equal work? So answer is no. So check P3. So and then request start with P3 is request P3 less than or equal work. Yeah, and then P3 less than 010, so means that no. The answer, and then check P4. Same thing, request type P4, and is request P4 less than or equal work? So the answer is no. So if no such PI exists, go to step 4. If finish equal false for some I, or for I value between 1 and 4, then the system is in deadlock state. Okay. So detection algorithm usage. If a deadlock is detected, we must abort, or they call here rollback. Otherwise, rollback some of the processor involved in the deadlock. Okay. So later we explain this. So need to decide when and how often to invoke the deadlock detection algorithm, which depend on how often a deadlock is likely to occur, and also how many processors will need to be rolled back. So one for each disjoint cycle. And if detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we will not be able to tell which of the many deadlock processes cause the deadlock. All right, so it become a problem right now. Yeah. So process termination about all deadlock processes. Okay, so this how to recovery from deadlock. So next we need to abort one process at a time until the lag cycle is eliminated. So in which order shall we choose to abort? Priority of the process, how long process has computed, and how much longer to completion, resources the process has used, resources process needs to describe, and how many processes will need to be terminated. Is the process interactive or batch? So, which order shall we choose to avoid based on the criteria here? Yeah, all right. So, and then resource preemption, selecting a victim. Okay, so mean we have to choose which one to minimize the cost. Rollback, so mean return to some state, some safe state. Yeah, safe state, and then by restart process for that state. So we start at the beginning, rollback. Where? Okay. Starvation, some process may always be victim as may be pick as victim. Yeah, include number of rollback in cost factor. Okay, can be happen. So a deadlock state occur when two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. Three principal methods for dealing with deadlocks. First, use some protocol to prevent or avoid deadlocks. Next, allow the system to enter a deadlock state, detect it, and later recover it. Yeah. And then next, ignore the problem altogether and pretend that deadlocks never occur in the system. Okay. So this is exercise in the books that you can go through this. Okay, end of chapter 7. All right, that's all for chapter 7. Thank you for listening and watching, and see you in the following chapter. Assalamualaikum and bye bye.